Welcome back. Let's talk about the oxidations with potassium permanganate. This type of oxidations are actually very similar to the ones that we talked about with osmium tetroxide, but there are some differences that we're going to need to highlight. First things first, kind of want to bring your attention to the type of material, how this looks like, and perhaps the solutions that you may have observed or made yourself in the laboratory. So potassium permanganate is actually a pretty reactive inorganic reagent. It has this kind of like purple, like black, coloration in the solid state. And when you dissolve it in, dilute enough concentrations, you can actually create these beautiful, pink solutions, which can also be served, for kinetic experiments and all the like, right? So that's kind of like a throwback to general chemistry. Um, but turns out that this reagent is actually kind of extra more reactive than osmium. In fact, um, you can produce the same products that you get with osmium tetroxide. Specifically, if you just react the alkene with one equivalent of potassium permanganate, you can get that same diol configuration that we talked about in the previous video. But the caveat is that this has to be done in under cold temperatures, right? So at the very least, you have to use an ice bucket, keep the temperature to 0 degrees Celsius, because permanganate is very prone to undergoing further reactions, and we're going to talk about them in a second. But if you do use potassium permanganate under basic conditions and the temperature is cold, the reactivity towards that alkene will be identical to that of osmium tetroxide. In fact, the only difference here is that instead of osmium, now we're just writing manganese 7 to begin with, which then accepts the 2 electrons that come from the pi bond to reduce the manganese 7 to manganese 5. And after that, you have to remove the manganese 5 to produce the syn diol organic product that we have here. Okay, now to give you an idea of what the fate of the permanganate reagent is, and this is actually something that I think it's important to kind of consider, at the very least, just to kind of know what's happening with your molecules, what's happening to all these elements. This is often something that gets kind of like, it becomes an overthought in most organic chemistry textbooks, and I think that's a bit of a shame. I think you ought to know a little bit as to what is, as to what is happening, and you have enough knowledge from general chemistry to actually understand what's happening. So I'm going to try to walk you through the process. All right, so once more, what we're seeing right here is the electron reduction potential diagrams of manganese and carbon. And on the top, we have the most oxidized species. On the bottom, we have the most reduced species. And the number separating the different intermediates, if you will, or the different stages of manganese in terms of oxidation, these numbers represent the potential values, the standard potential reduction values. And as long as you're going from top to bottom, the value tells you exactly what the reduction is going to cost. If the value is positive, the reduction is very spontaneous. It's very likely to happen on its own. If the value is negative, then the reduction is probably not going to be very spontaneous, but the opposite will be true. If this value is negative, then the oxidation going from bottom to top will be favorable. So starting with the reagents, and here we're gonna just look at methane, which is semi-equivalent in terms of the reduction value compared to the alkene. If we start with methane and permanganate, these things are very, very far off from each other. They don't even overlap. And what the diagrams are telling us is that they will have to react ultimately to give you overlapping regions. So in the case of manganese, we could go from permanganate all the way down to manganese 4 oxide and produce CO2. That's a potential product that we could make, right? And that will overlap the areas. Or we could even go to manganese 2 plus and produce permanganate. But between the different reagents, manganese 4 oxide is actually pretty insoluble, even in water. So the moment you form it, it precipitates out and kind of stalls the further reaction into manganese 2. But under certain other conditions, you can make this happen. Anyway, think of it this way. You take your manganese 7, which is permanganate, and you add 2 electrons from your alkene. So now you've reduced it to manganese 5, which are represented by the hypothetical formula right here. So this is manganese 5 with 4 oxygens, which technically will be called manganate. All right, now that based on the diagram, what we're saying is that this will probably be kind of like the manganese 6 species right here. It will probably be a hot species, metastable species that will disproportionate to give you manganese 6 and manganese 4, right? So that manganese 5 is going to be in shuffle a little bit to get you to more stable oxidation states. So we get, 1 part manganese 4, 1 part manganese 6. And notice that here on the diagram, manganese 6 is also metastable. So it will disproportionate into manganese 7 and manganese 4 as we see on the diagram. And in essence, the red boxes right here, whatever is next to them, on the top and on the bottom, those are the ultimate products of this species. So the manganese 6 will react to give you 2 parts permanganate and 1 part manganese 4 oxide. And at the end of the day, right, you produce a little bit of manganese 7, which is your permanganate that you started with anyway. But the ultimate fate of the manganese is just your manganese 4 oxide, which is this insoluble solid that it's formed, precipitates out, and that's the end of the story. All right, so as long as you treat your alkene under basic conditions with potassium permanganate and cold temperature, you will be able to basically keep the reaction to the point where you'll only introduce the hydroxyl groups on the positions that used to be the alkene carbons, and they will be positioned in the same configuration. But if you do not pay attention to the temperature, even do this at room temperature, will be enough to go much further than the syn diol configuration. In fact, if you heat this up, you can make it so that you end up producing more interesting products. Carboxylic acids could be some of them. You could also produce ketones, and one of them could even be carbon dioxide. And I kind of want to walk you through the process of how these products get formed. So here the double bond is completely broken, once you start heating this up. And this is because permanganate is a really strong reagent. From the point of view of redox, is very much on the lookout for electrons. It wants to acquire electrons, and the organic reagents are reduced versions of carbons. So those are the prime targets that permanganate will go after. So what I'm going to do right now is try to show you a pseudo mechanism, and I'm going to call it pseudo mechanism because it's not necessarily the true mechanism. This is the way I kind of think of the reactions happening, and not to say that some of the reagents don't get formed along the ways, or some of the products don't get formed along the ways, but this is not the formal official mechanism. But in most organic chemistry textbooks, the thing that annoys me about this process is that they'll tell you, okay, you have your alkane reacted with potassium permanganate and you get this type of products. Never ever do they address how does that happen, like what is the process. So I'm going to try to give you that context right now. All right, so first things first, your permanganate manganese 7 will react with the alkane. 2 electrons from the alkane will be provided to the manganese 7, reducing it to manganese 5, and you form this metalla dioxacyclopentane structure, okay, every single step of the way, right? Which is, if you keep it under cold conditions, the reason you end up with the syn diols. But then the thing is that you still have potassium hydroxide present in your solution, and so the manganese 5 is displaced by the hydroxyls right here, or the potassiums if you want to look at it that way, and the manganese 5 ultimately gets turned into manganese 4 in the manner that I explained a little earlier. So now you have these potassium diolates, which can interact with another molecule of fresh manganese 7 permanganate. So you can bind to the manganese 7 and via a few steps that I'm definitely avoiding here, which will be proton exchanges and hydroxyl eliminations, you end up replacing the oxos right here with the oxos of the manganese. So at the moment this is manganese 7, and manganese 7 is still very hungry for electrons, so it will try to take another 2 electrons from this molecule. And basically the way it will do it is by taking the electrons of the things that are closest to it, which will be the electrons of the oxygen right here. So if the oxygen donates those electrons to the manganese 7 to turn it into manganese 5, the oxygen will be electron deficient. To make up for that deficiency, the carbon-carbon bond that we see up here will be broken, and those electrons will be brought over to the oxygen to complete its octet. But if that happens, that means that the carbon over here is going to become electron deficient, which means that now the electrons of the oxygen will have to be delivered onto the carbon to complete its octet. And at the end of the process, what ends up happening is that you end up forming a ketone here on the left side of the molecule. And on the right side, you have an aldehyde, right? And notice that the groups are still there. You have methyl, methyl, so we still have methyl and methyl. And over there we had methyl and hydrogen, so we still have methyl and hydrogen. But we have oxidized them to the ketone and aldehyde state. Now for carbonyls that do have connections to just carbon, this is kind of the end of the story for them. But if the carbonyl is bound to hydrogen, well, something interesting can happen. Now, first things first, you bring a fresh molecule of permanganate to which the aldehyde can bind to, and one equivalent of hydroxide that can attack this carbonyl center to form a metallodioxacyclobutane structure, as shown right here. And like we saw before, the manganese 7 is still hungry for electrons, so if it can take electrons, it will do so. And the presence of this carbon-hydrogen bond is actually ideal for another oxidation to take place because, first of all, the solution is under basic conditions, actually pretty good basic conditions. So this hydroxide can attack this proton, and normally this proton wouldn't have a pKa that will be low enough for hydroxide to deprotonate it. But because this molecule is bound to the manganese 7 center, which is a really strong Lewis acid, you have a severe lowering of the pKa of this CH bond, and the hydroxide attacking this proton, basically what it does is it leaves these two electrons that now are going to move out of the way towards the oxygen, completing, well, now if that were all that was to happen, this oxygen will end up with 10 electrons. So two of those electrons get delivered to the manganese to leave the octet intact and without violation whatsoever. But that, of course, reduces the manganese to manganese 5, which ultimately will come off as manganese 4 oxide. But notice what's happening here to the organic molecule. Remove that proton, and all that's left over is this carbon, this methyl group bound to that carbon. But now you're creating a double bond between this central carbon and the oxygen. In other words, you have produced a carboxylate unit, which when you end up finishing this process by adding an acid, you'll end up isolating your carboxylic acid. And so what you can see right here, and this is what now the books will tell you. So everything that I've shown you right here on this slide is what the textbooks don't show you, which kind of drives me nuts. But at the same time, I don't want you to memorize this entire process. I just want you to kind of look at it and use it as a guidance, and perhaps to kind of appreciate the underpinnings of this reaction. There's a lot of stuff going on here, and there's a lot of good inorganic chemistry along with the organic chemistry that we're talking about. All right, so hopefully you can appreciate that. But the thing that's really important, and this is something I'm going to expect you to do, and the thing that the textbooks kind of expect you to do as well, is that when you look at the organic molecule you start with, the alkene that you started with, you're going to have one carbon end of the alkene that in this case has connections to two other carbons. So all that happens there is that you break this alkene open, and instead of having a carbon-carbon double bond, now you're going to have a carbon-oxygen double bond. And as long as the connections here are to other carbons, that's all you end up with. You end up with a ketone. But if you do have a connection to a hydrogen, like we do on this carbon on the right side, you break this connection of the carbon-carbon double bond and you write an oxygen instead to make your carbonyl. But if this is a hydrogen, you're going to have to replace the hydrogen with an OH, and so that leads you to the carboxylic acids. But the process that I'm showing you right here is, in a way, how this manifests itself in terms of the mechanism. But once more, I want to tell you, this is just the way I think of it. It's not the official mechanism. Okay, so let me show you this one more time. Now with an alkene, one of the most basic alkenes, ethylene. This doesn't have any carbon-carbon connections on the alkene carbons. So we're going to see what happens here. So the first step is still the same. 2 electrons of the alkene get delivered to the manganese 7 to turn it into manganese 5, while at the same time forming the metalla-dioxacyclopentane structure. Then the potassium hydroxides come over to substitute the manganese 5, and a fresh batch of manganese 7 or permanganate binds to this diolate organic fragment. 2 electrons are delivered to the manganese 7. In the process, this carbon-carbon single bond is broken. The oxygen delivers the 2 electrons to the carbon here on the right side to end up producing your 2 initial carbonyls. Now, because you didn't start with any connections to any other alkyls of any kind, all you have right here is carbon-hydrogen bonds directly on the carbonyl carbon. So what ends up happening is that when the aldehydes that you form, the formaldehydes that you form, interact with another fresh batch of manganese 7 and one additional hydroxide attacking it, you're going to form these metallocyclo dioxabutane structures, and you have fresh carbon hydrogen bonds to be attacked. So you're going to have the hydroxide attacking that hydrogen bond. The 2 electrons that made up that CH bond are going to be delivered to the oxygen down here, and the 2 electrons that made up the oxygen manganese bond are going to be delivered to manganese to make manganese 5. And in this process, once you remove that first hydrogen, you're going to end up with only one hydrogen bound to that new freshly formed carbonyl. So this is a carboxylic acid, but this carboxylic acid still possesses a carbon-hydrogen bond. So what ends up happening is that this formate molecule that we've generated is going to interact with a new fresh batch of manganese 7. And when that happens, along with one equivalent of hydroxide, you're going to end up deprotonating the second proton that was present in there. And then this will generate a new batch of carbonyl compound, but specifically you're going to generate this stuff. And at first look, you might say, oh, that's another carboxylic acid. But technically it is not, because this is not organic, this is now inorganic. In fact, this is hydrogen carbonate, which if you treat with acid, hydrogen carbonate will decompose into CO2 and water, right? So that's just directly from general chemistry. So the end result right here is that if you do have on your original alkene no carbon-hydrogen bonds, you're going to end up with a ketone, right? And you have to keep the structure of that ketone intact based on what the structure of the original alkene is, right? So that you don't get away with, right? It will be a ketone, but you have to have those alkyl groups present. If you do have a single carbon-hydrogen bond on the alkene carbon, then you'll end up generating a carboxylic acid. But if 2 carbon-hydrogen bonds are present on the same carbon of the alkene, then that carbon will be turned into carbon dioxide. And these are the sequence of events in which this entire premise takes place. Once more, this is the way I look at it. This is not the official mechanism, but it's somewhat close to it. All right, so the last thing we need to do is just show you what happens when an alkyne instead of an alkene is treated with potassium permanganate and under high conditions. All right, so here, same deal as with the alkenes. 2 electrons have to be delivered to the manganese 7 to give you manganese 5. And so when 2 electrons get delivered, the triple bond gets turned into a double bond. And now you have this structure with the 2 oxygens, the manganese, and the alkene fragment left over. Okay, now displace the manganese 5 with a manganese 7. And here you still have to supply 2 electrons to the manganese. Now, unlike the alkenes that we started with, this structure right here does have a double bond present, so we can donate those 2 electrons from the double bond without actually rupturing the carbon-carbon connection that we have in the organic fragment. So we're going to deliver these 2 electrons onto the oxygen. The electrons that were part of that oxygen-manganese bond are going to be fully delivered to the manganese 7, which will turn into manganese 5. And then the 2 electrons of this oxygen will be delivered to the carbon next door. And the end result is that we're going to have 2 new carbonyls formed like we did before. But the difference is that we haven't broken that carbon-carbon connection between these two fragments. All right, so this freshly diketone molecule will be now exchanged onto a new fresh batch of permanganate. And once more, the permanganate is want to acquire 2 electrons. Since we have hydroxides present, the hydroxides are very prone to attacking carbonyl compounds, forming these carbon-oxygen bonds, that carry the hydroxyl over. So what's going to happen now is that you take those 2 electrons. Here, the connections of those carbons will be broken. So you'll bring those 2 electrons over onto the oxygen. The 2 electrons of the oxygen-manganese bond will go to manganese. And then the bond right here will be delivering its 2 electrons onto that carbon. They used to be the alkyne originally. So what happens is that you end up forming carboxylic acid, and of course the manganese gets reduced to manganese 5 that ultimately ends up turning into manganese 4 oxide. But the end of the story right here is that if you have an internal alkyne, one that doesn't have a hydrogen directly bound to the alkyne, unlike the alkenes, the alkyne will give you a carboxylic acid right away. But if you do have a hydrogen bound to the end of the the end of the alkyne, then this will give you a carbon dioxide molecule in a similar pattern as before. And so this is kind of the thing you want to really memorize in terms of what product you're going to generate. You still need to pay attention to the structure of your alkyne and alkene, but this informal mechanism is meant to kind of give you an idea of what's happening and how you're forming these molecules. Okay. On the next video, we're going to talk about the last reagent that we use for oxidations, the ozone reagent. So I'll see you in the next video.